Hello, today we're going to be talking about deformation, mountain building, and what goes on in the Earth's crust due to the contact between the different plates. So rock deformation involves changes in the shape or volume or both of rocks in response to applied forces. Geologists use several criteria to differentiate among geological structures such as folds, joints, and faults. We'll talk about all those. Correctly interpreting geological structures is important in human endeavors such as constructing highways and dams, choosing sites for power plants. Obviously, what happened at Fukushima is a real problem, and finding and extracting some resources. Deformation and the origin of geological structures are important in the origin and evolution of mountains. And most of Earth's large mountain systems formed and in some cases continue to form at or near the three types of convergent plate boundaries that we'll talk about. Terrains, that's spelled a little different than when you normally think of a terrain, but terrains have special significance in mountain building. We talk about Earth's continental crust, and especially with mountains, what stands higher than the adjacent crust because of the compositional or the composition and the thickness of that crust. So here we have a picture of a sedimentary bedding plane. Obviously it's not flat, it's gone under some sort of deformation. So how does this occur? Well, we apply a stress, which is a force of deformation, and then the strain from the applied stress is a change in shape that results from, in this case it looks like it's coming from the sides. Could be, it's obviously from the top because it's up deep under the earth, but all this pressure will change the rock formation over a long period of time. It could be millions of years, or usually is millions of years that this happens. And deformation is a general term that we use in reference to the change of the shape or volume of a rock. So when it's folded or fractured in some way, we call that a deformation. This is usually near certain things like where plutons are, if you have volcanism, if there's metamorphic rock, there's continental plate boundaries, and there are a variety of places where this can occur, and that's where we are more likely to find these kind of extreme changes in the rock. So many of you are ice fishermen, and what happens when we subject ice to a force, it will stretch or bend, and that's called elastic deformation. If you achieve a point where the ice is no longer elastic, it can fracture, and obviously we can fall through. So this is a picture from your book, but if we know that we spread out that force so it isn't focused on one spot, we're unlikely to fall through the ice because the total surface area is increased when you lay down on ice and in this think I'd better belly squirm back to shore. So if you're ever in that position, you know what to do. So in this slide we see how types of strain change the formations that they are producing that strain on. So we get a compression strain where you have rocks are squeezed along the same line from opposite sides, and the compression shortens the rock layers either by folding or faulting, which means fracturing. So the one on the left is folding, the one on the right is faulting, and that's due to the elasticity of the rock. And then we have a tensional type of compression or strain. In this case, it's forces along the same line that act in opposite directions. This is something like the basin and range, which I have a picture of somewhere in here, where you get a stretching of the rocks, which opens up a little more space. They become less dense in a sense, and so the rocks fall into that density gradient and end up falling down and producing normal faults along those fault block mountains. And then we have shear, which is basically we have a force that is parallel to each other in opposite directions, and the deformation occurs along the slip in the different planes in those rocks, sort of like what happens in a card deck. I think that's what I have in the notes. And here's a graph of what happens. So you get rock deformation. You have two different sources of rock here, A and B. There's one rock that is quite brittle and it fractures without actually getting to plastic deformation. So this is elasticity There's some elasticity, but there's no change in the rock structure, so it's not plastic. And then it fractures. And then on the other one, A, is where it reaches an elastic limit, and then this sort of plastic deformation, and then there's a fracture. So if you ever go to the Henry Ford Museum and get their plastic injected molds, so you can get like the Wienermobile, and you can get some different, cars there. Basically what that is, it's a plastic, so they take something that is obviously molten. In this case, it's not molten, it's solid, and they inject it in something and it holds that shape once it's been changed, and that's called a plastic shape, because the plasticity is in the ability of things to deform and then hold the shape that you put them in. An elastic deformation is the ability of the rocks to be stretched and then return to their previous formation. So think about an elastic band. You can stretch an elastic band. If you release the stress on that elastic band, it will return to its normal shape. So most rocks will deform elastically till they reach a specific limit, and then they will start to deform plastically, and then they reach the plastic limit, they will fracture. But the stress that's applied will cause it to not return to its normal shape. So if you release the stress after it's gone through the elastic limit, it will remain deformed. Elastics actually have an elastic limit, and that's when they snap. But this is determined by, meaning if it's how it takes, if it's an elastic type of limit, or if it's actually just elastic deformation, if it's brittle, or if it has plastic deformation, is dependent upon the type of stress that's applied, pressure and temperature, the type of rock, the length of time. That's a biggie, how long they're actually under the stress. And then ductile rocks, which can take a great amount of plastic strain, which means they bend, of course, and they won't fracture, where you have other rocks that are very brittle and they take a small amount of plastic strain, or actually no plastic strain in this case, and they fracture before they even deform. So we get different formations depending on what's going on. In this case, we have strike and dip, and this is the orientation of the deformed rocks. So here we have a monocline. Let me get a pen. We have a monocline, which means it has one side to this deformation, and we have, well, you see a principle right here. It's called the principle of horizontality, which means that all rocks are originally laid down horizontally, or in this case, it's almost horizontally. You'll see these layers go in this direction. And anytime you see a layer come up like this and bend, like we have here, this is a very good example. It's coming along like this, and then it bends down this direction. They're inclined, and we see that that's a result of either folding or fracturing. And there's going to be a certain strike, which is the face of the hill, or the angle at which it's, that's protruding, and then the dip, the angle at which it's going into the ground. Which leads us to this slide of a strike and dip orientation for deformed rock layers. In this case, we have a rock structure that is sandstone, shale, sandstone, etc., and it's coming up to the surface at a 40-degree angle. That's what this is right here. That's 40 degrees. And then this strike, which you see right here, that's the face of the hill. If you were standing on the hill right here, right, standing there, and you're looking this direction, in this case, the strike is 40 degrees, right, southwest, and no, not 40 degrees, I'm sorry, the angle's 40 degrees right here, but you are seeing that the strike is facing, if you were to look to the left along this flat surface, that it would be to the southwest, and then this would be the northeast, and that's on a simple compass, right? North, south, east, and west, and then we have these coming off this direction, which is what you see there. This is southwest, and then this is northeast. And of course, that's what you see here. You also have southeast in this direction, and northwest in this direction. And basically what it is when you look at the dip, or the strike in this case, the strike and the dip, you're looking at the rock layer's orientation with respect to the horizontal. So the strike is 40 degrees up, that's what that 40 degrees is, and the dip is 40 degrees down. And basically this is an inclined plane. Another deformation that we will be looking at is faults. And I would ask you, if you were in my class, is this a normal or reverse fault that you see on the left? And it says a normal fault, so I gave it to you. This is in Death Valley, and what it means when you have a normal fault is the hanging wall, which is the one that would be if you were standing here and it's what is above your head. So if you're standing right here, right, and you look up, this is what they call the hanging wall, which means you would hang your lantern on it, and that goes back to when we were actually, mining in faults before we had the modern machinery that we have today. So if you were in California and you had a gold mine, you would go in the fault because it's the easiest thing to remove all the rubble because it's already been broken up by the mountain rather than having to break it up by hand. If you took a rock pick and tried to break up the solid mountain, it would take forever. So they have these terms called the hanging wall. So this would be the hanging wall, and that's the one you would hang your lantern on, and this is the foot wall. That's the wall that you walk on. In this case, I'm going to put a big arrow right here. The hanging wall is moving down with respect to the foot wall, and you can see that by this structure right here, this brown structure, and this is the hanging wall. It's the same structure, and it's moved because of the fault, and that's why it's called a normal fault. And this over here is also a normal fault because it's moving down, right? With respect to the hanging wall, if you were to be standing right here, looking up, this is the wall over your head. That's the hanging wall. And then, of course, we have that looks like some extreme folds. It looks like from the Balkan Mountains. It says right there, and that was the one we were looking at originally in Serbia. So folds in the rocks are layers that were once planar or flat, and then they become bent or wrinkled or something like that. And folds form because during compression they undergo plastic strain, which means they don't return to normal. And it usually occurs in rocks that are ductile. So think of, like, metals are ductile, and that's why we make wires out of them, because we can stretch them out and they retain that form. They have a lot of plastic deformation abilities, extremely so for gold. That's why it's worth a lot. Plus people like it because it's pretty, I guess. But anyway, so there are three kinds of folds that we're going to be talking about after, and we'll talk about the faults too. But the next folds we're going to talk about are monoclines, anticlines, and synclines. Now these are going to be a little bit confusing, but as I lecture, I think it'll become understandable. And here in this slide we have a picture of both anticline and syncline. So you have this axial plane which cuts through the middle of the bend, let's say. So here we have the axis of the bend. In this it's reversed, right? So you see the hill right here, there's a hill right here, there's a dip right here, there's a dip right here. So it's reversed in the picture, but I think you can see what's going on. So we have two arms coming off from the axial planes. We call those limbs, just like you would say your arm is a limb, right? And this is a limb right here. And this would be an anticline. So an anticline, that's right there. Anticline means it's going down. Incline means to go up. Anticline means to go down. Syncline means with hill. That's what that means. So syncline is where you're at the bottom, and in order to get to where you want to go, let's say out of this bottom, you have to walk uphill in both directions. That would be a syncline. It's with the hill. This is against the hill, which means that you're going down. And in this case, we have an anticline right here and a syncline right here. So it's a little different. I guess I could have probably drawn those a little straighter. Whoops, I just deleted that picture. I brought it back. So anyway, that's funny. So folds of the axial plane and divides the fold in half. Each half is called a limb, like I said, and there's an imaginary line that forms the intersection between the axial plane and the fold in the bed. Sin is with, so you're at the bottom of the hill and you go up. Anti is against and you go down. Here we have a picture, a deformation of a monocline. We saw it before. Again, they reversed it for you. It's just the way they're doing it. And we have, in this case, we have one arm. So this may be at one point, it'll travel wherever it's going. But in this case, we have one arm, one limb coming off, and there's no limb on the other side. That's called a monocline, and it's something that is usually horizontal, but then has a uniform dip in one of the limbs. So one limb is horizontal and one limb is dipped, and the fold of the axis is on the incline. So right here, and then the fold is right there. You can see it right there. So this is the axial plane right here, cutting through this. There's a reason we want to know what a syncline and an anticline is. So in this case, we have the anticline. So if you were to take and draw a line through here, here's another anticline right there, and there's an anticline right here, and then there's the syncline in between those. And these are with, and you know that in the syncline or the anticline, depending on where you are, you will know that you're either an old rock or a young rock, younger, I guess, and that's dependent upon the fold. So you see the folds going up, not the folds, sorry, the layers on the side. The layers are laid down in sequential order. So the ones on the bottom, these are older than the ones that are at the top. These are younger, right? And because they're laid down that way, when you look at the wrinkles, you'll notice there's a layer right here, and that's younger than this layer that's exposed right next to it. And what you see in these numbers are the strike and the dip. So depending on which direction the hill is, right? The hill's going up, the hill's going down, and then the strike is in this direction. This is another strike that is southwest by northeast, and you have a 50-degree slope in this case. And you know that along the anticline, where the axial plane cuts through it, it's the oldest exposed rock, and then on the syncline, so here's the anticline, and then on the syncline, that's the youngest rock, or younger than the older rock that's exposed next to it. And as we move forward, you're going to see that these kind of get crazy. So what you have here is, as these things get turned over under the earth, you end up getting the axial planes turned to the side, because if you have equal limbs going off in both directions, right, at the same angle, in this case the axial plane is actually at an angle because of that. And here we have a strike and a dip of 55 degrees and a strike and dip of 20 degrees. And if you look at this one here, these are actually overturned. So when you say overturned is the axis and the axial plane, you're going to reverse the age of the rocks depending on what's exposed. So, and they do it by showing you that there's a flipped layer of rock, that the age of the rock is going to be younger or older depending on how the anticline or the incline is flipped. In this case, you have an angle of 75 degrees, but it's 75 degrees and it's been flipped and it's at 75 degrees. In other words, when you flip this weird flipped symbol right here, because you flipped over the layer, you have limbs that are dipping in the same direction due to extreme folding, I think is probably a better way of saying that. And then we have these, it gets even crazier if you overturn and then you expose layers that originally were laid horizontally and now they're vertical. This is called recumbent. You end up with the axial plane that is basically now horizontal to something that was an incline, or the axial plane is now the horizontal plane, but we know that the bedding plane is now vertical. So because it's vertical, it has been turned over in quite a dramatic way. So the axial plane becomes horizontal, or nearly horizontal, and then the bedding plane, the stuff that was laid down flat, becomes vertical. And that usually happens at convergent boundaries because of extreme pressures and shifting in the rock. Here we have deformation of geological structures that gets into not just the folding on a horizontal plane with an axis, but the axis actually is not horizontal and it starts dipping because of, obviously this is on a sphere. The Earth is spherical, so it's not truly flat, and so you end up getting these strange dips. And this is called a plunging fold, and they erode. Really what you're looking at is how old is the rock, what do we expect to find, are there fossils, etc. And you want to figure out, if you discover a really famous fossil in this area, and this is the youngest exposed rock, rather than this, which is exposed, it would be older. You want to make sure that you can date it properly, or you're discovering something and people understand what it is you're doing. And here they have what they call the plunging syncline and plunging anticline. Again, the anticline is right here, syncline is right here, anticline right here. And this is a picture from your book, and this is a real plunging fold. This is what we just looked at. And you'll notice this rock right here is younger than this rock up here because of the fact that it's a plunging fold, which is a little confusing because usually you think the rock layers that are higher are younger, but in this case this is older up here than this rock layer down here. And this has got to be Wyoming because I used to live in Wyoming and it looks like that. But it's pretty cool, pretty desolate, desertified, but it's pretty cool. And we have this, which you all should recognize, at least the one on the bottom. The one on the bottom is Michigan, or the Michigan Basin. And we know if you go up by the Palm in Michigan, where Mount Pleasant, or where the mountains a little farther north from there, you will see the youngest rocks that are exposed in Michigan. And if you're on a dome, the oldest rock, because of the erosional features, the oldest rock is exposed at the middle. And of course in Michigan the youngest is exposed in the middle. This is just a dome or a basin. And this is a result of folding rocks. There's no plunging folds here. It's just a circular deformation around one spot. Which leads us into different characteristics of what happens when you undergo strain and stress in rocks. And there are joints and fractures that occur. There are faults and there are joints. And here we have joints. This is the Causeway of the Gods, I think. You have to look in the book, but that would be in Ireland. This is basically where lava cools, and as it cools in such a way that it produces these joints in the rocks, which are the same sort of figure, basic figure. They're six-sided usually, and they look, basically the same. I find this stuff up in Colorado whenever I do research on the side of the weathering mountains, the weathering and eroding mountains. Usually lava tubes or volcano necks. But these are not faults. They don't travel through the whole bedding plane. It's usually just on the surface. And they form in response to, compression, tension, shearing, and fracturing of the rock. And they may go through 1, 2, or 3 layers, depending on what they're forming in, but they do not go through the whole structure, which is what a fault would be. Which leads us to this picture. And this is a fault. Again, this is a normal fault because the hanging wall has moved down with respect to the foot wall, or the wall that you hang your lantern on has moved down with respect to the wall that you would be walking on if you were mining this fracture, which means if you're standing here, you were to look up, the wall that you hang your lantern on has moved down with respect to the wall that you would be walking on. These are called dip-slip faults. Obviously they're slipping and dipping, and the strike is the direction of the fault. Right? It's traveling in the mountain, whatever direction. Again, this is a southwest northeast strike, and it's a fault plane. That's what we call it. Most dip-slip faults are categorized as normal or reverse. There's one extreme fault that is still categorized as a reverse fault, but it's pretty extreme, and we'll see it in a little bit. It's still a reverse fault, but they call it something a little different due to the angle of the fault formation. And just as a recap, this is a dip-slip fault. It's a normal fault because the hanging wall is moving down with respect to the footwall. So the hanging wall is moving down with respect to the footwall. And then we'll call this the strike is the fault scarp. That's the strike right there. Here are the fault block mountains. This would be in Nevada. And these mountains are the result of tensional forces pulling apart the rocks. And as the amount of force pulls these apart, the density drops a little bit, and the space, there's more space here. And so you get these normal faults between the mountains in the valleys. So here you see this would be the fault face that you're looking at. Well, I can't draw straight right here. And this would be one of these horse that you're looking at. And this is the graben. And what you're looking at, this is a normal fault. This is the strike, but this is the normal fault right here, producing this mountain. Another fault that's a dip-slip fault is called a reverse fault. And in this case, the footwall is moving down with respect to the hanging wall. It's the reverse of the normal fault. That's why we call it a reverse fault. And in this case, the fault scarp, you don't really get a fault scarp, you get just a layer of rubble because the hanging wall is moving up, and as it moves up, stuff just falls off of it. And it's fairly easy to see if you know what you're looking at, but it's a little bit more difficult to get the angle on these because of the nature of how they erode. And this is a dip-slip fault. We call a thrust fault. In most cases, we just call them normal and reverse. This is just an extreme reverse fault, where it's the thrust fault is 45 degrees or less. They can be as low as 5 degrees, which means as this moves in, you basically pile up a bunch of rubble. Big, huge area of rubble zone that's in front of this fault. And then one of the more famous types of faults is the strike-slip fault. So the strike-slip fault is where you have two plates or areas where they're slipping past each other, and these are can produce some pretty extreme earthquakes. Well, that being said, but there's a convergent boundary in out from Argentina and Chile that produces some pretty extreme faults, and that's just a normal fault that's being produced there. But faults in this strike slip orientation are when they actually strike or hit each other and then they slip. That's why we call it a strike slip fault. And this is either a right lateral or a left lateral depending on the direction of the offset between the blocks. So we have the San Andreas fault, which is the most famous one, which I have a picture of from the book that's here. And this has been going on, for 25 million years or whatever. And you'll see the different kind of, so here we have, this has moved this far, it's moved very little from the smaller stream here, but if you'll note there are marks here, which in reality were over here at one point, so it's moved quite a long distance and there's no longer a stream there, but there's some apparent movement in this fault that we can see, And this erosional feature here, it's pretty, it's pretty dramatic that you don't get any erosion, and it's stopped and it moves enough where you don't erode through that barrier, which is the fault itself. And then you have the oblique slip faults, which are basically strike slip faults, but they also have a dip to them, which in this case you can see the fence coming down here and then it doesn't meet up over here, so this is moving in this direction and down. So this would be a oblique, or both a dip and a strike. So here's the fence line coming down like this, and then it's over this direction, right? And then the fence line comes out like right there. So they have components of both a strike slip and a dip slip for movement. Which leads us to this slide on mountain building. We have the Horst and Graben, and it's an area where basically you have to stand 300 meters above the surrounding terrain or surrounding country. And it has a restricted area where there's a summit, and we can get linear peaks and ridges formed together, but there's a summit there, and the mountain system itself is basically a whole arrangement of peaks and ridges. So we know about the Rocky Mountains. That's obviously a very famous one, and that's due to the results from the plate movements, interactions along the plate boundaries. The Rocky Mountains are kind of interesting because they're such an extreme example of the interaction between plates, where the Rocky Mountains are quite far into the continent. Usually it's much more closely associated with the edge, sort of the Sierra Nevada type of range. But the Rocky Mountains, they've been building for about 80 million years. The Sierra Nevadas and the Rockies are still building slowly, and they will probably stop forming in 20 million, 25 million years, and they'll erode. So if we look at the Appalachians are, started forming 250 million years ago, and they got bigger than the Himalayas, and they've been eroding ever since, probably 200 million years since Gondwanaland or Pangaea broke apart, and they've been eroding ever since. Mountains form in a variety of ways. Mountains form through volcanism. There's some erosion. In this case, it's tensional forces because we're looking at basically the Great Basin. And you can get some compression, which is this, movement of the plates together. And then the fault blocking, which is tensional forces as they move apart or stretch. So how does this, it's called an orogeny, like Oregon, that means mountains. And it's an episode of mountain building. And orogenies are produced by convergent plate boundaries, usually where one is subducted under the other, which is what you see here. This is an oceanic plate boundary, and what happens is as one subducts under the other, you get this arc of islands, which is this right here. You get this arc of islands, and the arc of islands build up, and as that material comes to the surface, it's changing in density. So what you know about rock formation means that the silicate concentration of these volcanoes, as they get bigger and bigger, because the density is changing, they will get less. So here we have an example of that isostasy question, or the principle of isostasy, where we did the lab. And it's the idea of floating continents, and what's going on when something that is less dense is on top of something with a higher density. So the continental crust is less dense. We know that by looking at the rocks. We'll do a density lab next week. We're doing the soil lab this week. And we know that it's much thicker, and it explains why mountains stand so high on the continents, much higher than they do in the ocean basins per se, although Hawaii is the tallest mountain in the world, but that's because the oceans are deep. And the principle of isostasy basically says that the Earth's crust floats on the denser mantle, and there are two models out there, the Airy and Pratt model. The Airy model states that mountains have a low density root that allows them to project both far above and below the surface, this is the one on the right, And then the Pratt model states that mountains are high because they are less dense than the adjacent rocks like the mantle and the ocean crust. And both these models will explain how mountains are tall. But we have done experiments where you look at a plumb line. If the mountains don't have a root, and due to densities, you'd expect the plumb line to move so far. If the mountains have roots, then the plumb line would move half the distance because, in this case, the plumb line is attracted to the mountain, which is very big. In this case, the plumb line is attracted to the mountain, but it's also attracted down to the root, which is down there. But then there's some experimental evidence for this about how this works. Which leads us to, how do mountains float? I've already given you that when we did the isostasy lab, it's the same thing. One Yamato class battleship weighed 70,000 long tons, or 163,520,000 pounds. And the question is, well, how does it float? And the density, basically the density of the ship is offset, or the weight of the ship is offset by the space you have in the hull. The hull. So if you look at a ship, the amount of space that's inside here displaces, we have the water line, displaces more water than the weight of the ship, which is Archimedes' principle. It's also why icebergs turn over. You load it. This is a picture from the book, I believe. Not, I don't know where I got it, but I'm pretty sure. Yeah, it is from the book. If you look at an iceberg will melt, and the idea is that the ice will displace the amount of water, or the weight of the ice. We know that it's less dense than the water around it, and if this melts, the top is going to be smaller, or sometimes they turn over, and that's a result of how they float. But basically there's going to be the same ratio, what this is showing you, and that's something we should have got from the lab. I hope you guys noticed that when I was talking about it, is the ratio of wood should not change. If pine is a certain density, it'll float at a certain ratio, like 1 to 3. So in this case you have one measurement, whatever that be, say 1, I don't know, meter, and then below this there's going to be 2 or 2.5, and it'd be, just say 2 meters. If you look at this, this is going to be 500 centimeters, and below that there's 2 500 centimeters, or 1 meter. And the idea is that they float, they operate under the same conditions. Which leads us into something called isostatic rebound, which is where as the crust erodes, the low density roots will return to normal, so they reach an equilibrium level. We see this in Alaska and Europe and here in Michigan. When we remove this ice sheet, the ice melted fairly rapidly, and the continents are still rebounding. And we know that in Scandinavia, they're rebounding about 1 meter every century, which is pretty rapid. It's much more rapid than you build mountains, but it's still pretty interesting. If you look at deformation, is a general term that we use for any change or shape of the volume of rock, such as when a rock is folded or fractured. We have the principle of original horizontality, which states that most rocks are originally laid down horizontally. We have an elastic limit. We also have a plastic limit, which I didn't talk about as much, but rocks will deform elastically until they reach their elastic limit, and then they go into a plastic change, which means once they're deformed, they stay that way. Then faults or fractures along with the opposite sides have moved relative to one another and parallel to the fracture surface. We have the orogeny, which is an episode of mountain building. We have principle of isostasy, which is Earth's crust floats on the denser mantle. And then we have isostatic rebound. When large glaciers melt or mountains erode away, the crust rises back up to its equilibrium level, just like we see with Michigan.